get started. Okay. Hi, everyone. My name is James Skelton. I am the technical evangelist for Paperspace. Welcome to today's Tech Talk, where we're going to be talking about DALL-E Mini, aka Crayon. It was renamed recently. A powerful image generation model in a, or powerful image generation in a tiny model is the title. If you're not familiar with Paperspace, we are a platform for building and scaling machine learning applications. We have three different main products with Gradient, which is our MLOps platform, where you can explore a new library or dataset in a notebook, automate pre-processing, training, or testing with a workflow, and bring your application to life with a deployment. We encourage you to join our massive community and get playing around with our really cool tool. If you're anything like me, and when you need a GPU on the cloud in a pinch, you're using AWS or Colab, like I was before, I highly recommend trying it out, especially for the free GPU access, which is a bit more powerful than what you can get with Colab. All right, well, enough sales pitch. Let's get into it. So, as I said, today we're going to be covering DALL-E Mini, aka Crayon. There's a few things that we need to get through in order to really understand how that works. So we're going to start off with an introduction to the DALL-E framework. That's actually a typo, I'm sorry, the DALL-E 2 framework for image generation. After we've covered really what's going on there, how it works, we'll then jump into introducing DALL-E Mini. We'll talk about how DALL-E Mini was made. We'll talk about the reasons Crayon or DALL-E Mini was written in JAX, which is the Python library that it was written in. Then we'll break down how DALL-E Mini Crayon works and talk about some of the architectural differences between DALL-E Mini and DALL-E 2. There's a few other slides that didn't make it into the overview, like covering like use cases and things like that. So without further ado, let's move to the next slide. Okay, so because of the nature of this demo, it takes a little bit to get started. So what I'm going to do now is walk through how to set up the notebook for those of you that want to follow along with me. And then once we have the notebook all set up, we can actually get into the rest of the code while everything is setting up. So I'm sorry, not the rest of the code, the rest of the presentation. Then we'll jump back into the code after the presentation is over and see how Crayon actually works in implementation. So to actually run the demo, you need to have a Gradient account and the ability to run, so therefore the ability to run a Gradient notebook on one of our free GPUs. You also need a weights and biases account and API token to run Crayon. I tried to code this out because I figured that may be a blocker for some folks, but it's hard coded in there. It's an integration. So you need the API token in order to download the pre-trained models that are being leveraged by Crayon. Cool. So let me get out of the share screen. Because the code to set up the notebook can, oh yeah, I already went through all this. So to actually do it, you can do one of two things. I would recommend the first, which is listed out, but I'm going to put in the chat two links. The first is what we're going to use as our workspace URL. This determines what files will go into the Gradient notebook. And I've also included the link to my own version. You can follow along offline here, or you can fork it to your own account. But I recommend you follow along with me and make your own. So let's do that now. All right, so here's my account. I'm going to go into my project here, which it's just called Uncategorized Notebooks. And then I click on Create Notebook to get into the Create a Notebook menu, UI, I suppose. Here, the first thing you want to do is make sure that you have the PyTorch runtime selected. That's what we're using for this machine instance. Next, go to select a machine, and then it seems that the free GPUs are currently unavailable. This happens sometimes at midday, so sorry about that. If you are unable to follow along, you can still see everything on my screen and the offline view, and you can check back later today. They usually come back up in the afternoons, after work hours, things like that. For now, just pick the cheapest one or most expensive. You can use whichever choice you prefer. Okay. So some people can get the free GPU. It may be because I'm on a growth account, which lets me access these more powerful GPUs. So just for funsies, I'll click that. A180 gigabytes. Then down here in the bottom right, there is this toggle called Advanced Options. Let's open that up. And then that link I sent, the very first one, we're going to paste here in this field called Workspace URL. So that way, the files that we have in this repo, which is right here, it's our fork of DALL-E Mini, will be used in the repo. And actually, okay, sorry, there's an update. I wanted to make sure that went through. All right, so once you have selected this runtime, picked a machine, and most importantly, put this as your workspace URL, click Run, Start Notebook. And I'm not actually going to do that because I am on here already. Once you are in the notebook, which will take about 45 seconds to a minute and a half to spin up, if I had to guess, you can then click on this ironic notebook, IPython notebook file, I suppose you would say, and then scroll down here to the second cell. And then we're just gonna run everything between here and this cell that starts with load models and tokenizer. This will install all the prerequisite packages and make sure all our setup is ready. So we've got JAX, I'm drawing there's a corresponding JAX library I can't remember the name of. I think it's JAXlib that works together with it. Sorry, but that's what the second line is installing. Then we're going to install DALL-E Mini, and we're going to install VQGAN JAX from a GitHub repo. Then we'll just define some variables that'll help us download everything from WANDB. And then I've got some checks right here. This is just to make sure that JAX is pointing to the GPU. We've had issues in the past where that didn't work. And then make sure you comment out these two cells and run them as well. I just realized I hadn't. They are absolutely needed for everything to work. I got a good question in the chat about asking for where they can get the API key. That is literally perfect timing. I am going there now. So once you get here, this is where the API key comes into play. This is going to ask for your API key so that it can download the models. So what you can do is go to wandb.ai, and then click on the top right corner on your, you have to make an account, but once you make an account, which you can do for free, click on settings, and that'll take you here, and then scroll down, and I'm not going to show my, it's only the first 5 digits, it's fine. Scroll down here and you can get your API key. I'm not sure if it comes with it or if you need to click new key, but if it's not there, click new key, and then you can just click that to copy it. Okay. Can I get B's in the chat that everything I said follows, and then I'll give you, it may take a minute to make the weights and biases account and everything. So in the interest of not running out of time here, I'm going to continue the presentation. This is going to be recorded and uploaded to YouTube. So you will be able to follow along then if you cannot right now. So no worries on that front. But make sure that you run everything up to this cell with load models and tokenizer with the API key. This will just make sure that, oh, you know, I'm sorry. I take that back, actually. There's one, we have to also get the Dolly BART model. So make sure that you also run this cell, but it doesn't take nearly as long. So sorry about that. So make sure that you run up until this text prompt markdown cell, or the code cell immediately below that one. Then right after that, we get into the image generation part, which we will return to later. Okay, sorry about that. Can I get B's in the chat that everybody followed me there and that we are good to go? On to the slides. Cool. Quan, that emoji B. Don't see any files after the machine started up. Daniel, that I'm not positive this will work, but try clicking on the terminals button, which is right here, and then clicking plus. Sometimes adding the terminal will make the GUI like start displaying the kernel information. Not sure why that happens. I'm sorry you ran into that. Otherwise, I think we are. Oh, actually, another thought, Daniel. What browser are you using? It may be your browser. Have had issues with. Oh no, it shouldn't have that. I've had issues with Edge before, but not Chrome. Although I think they've patched out the Edge problems already. So I don't know. If you're still having problems in a little bit, okay, beautiful. So if you can't see your files, click plus on the terminal and it will add the files. Cool. Let's get back into the slideshow. Got a lot to cover. Want to make sure I get through everything. One moment. Cool. All right. So when I was doing my research for this, I came across the information about DALL-E Mini and just the general release notes and things like that. And I saw that it was based on the idea of improving the original DALL-E and making a smaller version. In the interest of keeping us as up to date as possible, though, I wanted to talk about DALL-E 2 instead so that we can compare and contrast how these two of these newer versions of the DALL-E thought process work. So just to clarify, DALL-E 2 kind of isn't really one-to-one with DALL-E Mini. There's some pretty major differences that I'm going to go over, but I think it works as a nice contrast, especially because DALL-E 2 is so much higher quality than DALL-E 1, as we can see from the image at the bottom here. It really is a huge step up in terms of FID. Okay, so that's my explanation. Let's get with the introductions. So DALL-E 2 was first introduced in the paper Hierarchical Text Conditional Image Generation with Clip Latents on April 6th of this year. It's considered one of the state-of-the-art models for image generation, trailing really only Google's Imagen and Make a Scene in terms of quantitative measurement FID. In terms of qualitative, I've found that they're all very comparable. DALL-E 2 is fantastic. Oh, I actually don't have that on the top of my head. Somebody asked me what FID means. Sorry, I should have had that. That is the Frichette inception distance, and it's just a metric for evaluating the quality of generated images, and specifically for GANs. So Yeah, it's a means of comparison between different image generation paradigms. So next, DALL-E 2 itself leverages clip and an ablated diffusion model to unify textual and visual information, and then learn to reproduce the salient features of the text and image data in a novel image. So that was a mouthful, but basically what it can do is it takes these two components to combine the information of the visual and textual inputs, which are a caption and the trained images that it's learned, or well, the encodings, I should say, and then learn to reproduce the salient features that are described by the encoding and correspond to the text in the form of a novel image that differs from the original. So in this example, we have a painting of a fox sitting in a field at sunrise in the style of Claude Monet. And we can see that this is very clearly a painting of a fox in a field in the DALL-E 2, less clear in DALL-E 1. We can also see these individual brushstroke kind of style, so to speak, that DALL-E 2 is able to impart because of this Claude Monet, less so with DALL-E 1. So what we have is a really powerful way to do guided image generation. And the way it's guided is using this model called CLIP from OpenAI. So CLIP is it's really what ultimately determines how semantically related a natural language snippet input is to a visual concept, because CLIP is able to learn the link between visual textual semantics and their visual representations. So in a nutshell, what happens in DALL-E 2 with CLIP is first, all the images and their associated captions are passed through their respective encoders, which is mapping all the objects into an n-dimensional space. Then they get the cosine similarity of each image and text encoding pair. And then the training objective is to simultaneously maximize the cosine similarity between incorrect coded image caption pairs and minimize the cosine similarity between the incorrect encoded caption pairs. So basically the encodings will match up or they won't. And what it does is it tries to it essentially ranks the more correct ones and then uses that to get its final output encodings. It's proven time and time again that it is very effective for guiding image generation processes, and you'll see it a lot. I mean, if you've been attending my tech talks, you'll know that it's frequently implemented in these image generation processes because it is just so good. And on the right, we have a visualization of what I just listed out a second ago. As you can see, all the images and all the image is encoded, the text is encoded, then we make pairs, and then we identify the best pair using cosine similarity. So once we have all the visual and textual data encoded, we get to the second part of DALL-E 2, which is Glide. And I actually hosted a tech talk on Glide in, I believe it was March. So if you go to YouTube, you can find a recording of that if you're interested. It's kind of the predecessor in a way to DALL-E 2 because they implement an augmented version of Glide to handle aspects of the image generation process. But anyway, the modified Glide learns to generate semantically consistent images that are conditioned on those CLIP image encodings. So we had said here these encodings, and that's passed on to Glide, excuse me, the all capitalized words. The model needs to learn to reverse the image encoding mapping that CLIP just learned via Glide, which it does through what's called an ablated diffusion model to learn how to maintain the salient features of the image for reproducing the image through gradual noising. So what this means is it has your sample image, and then it has a completely noised image. Then it completely noises the sample image, or sorry. excuse me, we have our sample image. It is completely noised, and then it through diffusion works backwards to recreate the salient features that were in the image and also in the image encodings. Sorry. So we start with a very noisy image and we end with something that approximates the input. Next, this process is stochastic. Reverse diffusion is the name of the process. And that means it's really nice for making multiple variations of the same kind of image output because on the same image encoding vectors. So basically what that means is if you wanted to run Glide multiple times and get significant variations, it would be able to do that. It wouldn't just give you the same output every time. This is a trait we see in quite a few image generation models like Pixray, for example. So how exactly does that work with Glide? This here is the process for the Glide ADMs. We see we start with this noised, then it works towards the X0. The process for the Glide ADM really is as follows. In order to add textual context to the diffusion process, DALL-E 2 first creates text to condition the image on. So that was this original sentence here, an image of the face of a man. Then encodes the sequence into tokens, which are represented here by these blue squares. These are then passed into a transformer, which is used to generate output tokens, which are then, as the process goes, it iterates and conditions on the final output token to create the textual encoding that works with the image. Oh, sorry, that was poorly said. Sorry, let me just start over. So it first creates text to condition the image on, then encodes the sequence into tokens, then it passes the tokens into a transformer, generates output tokens, conditions on that final output token, and then concatenates the projection of the final token embeddings to the attention context, so that the diffusion model is able to apply attentional changes to its image denoising process, and so that just, we'll add features or remove features, whatever's needed, to the tune of the inputted text prompt. Because that final token in the diffusion process represents an approximation of our original image space plus the textual features we want to modify it with, we can influence our image generation by altering it based on that relationship. Cool. And finally, so in order to inject that text conditioning information from our prompt into the image generation process, we leverage the clip encoder, image encoder and diffusion model they call diffusion prior. And the steps for doing so are as follows. So this is to get the image encoding that, sorry, no, this is, excuse me, it takes the image encoding with it from the, it takes the text encoding that we created here to use with the diffusion prior, which is pictured here. Excuse me. The steps for doing this are as follows. So we start out with the tokenized text and caption as to input. We make the clip and text encodings. We create an encoding for the diffusion time step, pass the noise image through the clip image encoder, and then output the final encoding, whose output from the transformer is used to predict the unnoised clip image encoding. This is then passed to the prior to influence the generation process. Okay, so that was a lot. At the highest level, just to overview what I just described for all of these steps, first, the clip text encoder maps the image description into the representation space. Then the diffusion prior model, diffusion prior maps from the clip text encoding to a corresponding clip image encoding. And finally, the my goodness. Finally, the modified glide generation model maps from the representation space into the image space via reverse diffusion, generating one of the many possible images that convey the semantic information within the input caption. So that's here. So I think this might have gotten out of order. I'm sorry. Excuse me. That explains some of that confusion. So I would, if you go back and review this, I would put this slide in front of this slide. So excuse me, I'm sorry about that. That must have gotten mixed up at some point. Cool. So now that we are through with DALL-E 2, we can start looking at DALL-E Mini because we have a sense of understanding and a means to make a comparison between the two. So DALL-E Mini is very exciting. It was developed this summer, really a few weeks ago. It took the internet by storm. If any of you are on a lot of social media or anything like that, you might have seen people posting pictures that they just were able to generate, like really random pictures. I know I was seeing it everywhere. Really common one was with BoJack Horseman. I don't know why. But it was developed in a collaboration between teams from the Google Cloud team and Hugging Face for Flax Jack's Community Week. I'm going to post, I have a link in the last slide to get access to this page where they talk about the project, and I definitely recommend looking at that afterwards. Their goal for making DALL-E Mini, which is also known as Crayon, by the way, just for any confusion, it's out there. They had to rename it so that there would be less confusion with the two DALL-E models. Because while they're related, they're not owned by the same people. But their goal was to reproduce the DALL-E level image generation with a significantly lighter architecture. So they wanted to make it much, much easier to run on much smaller GPUs, so much less costly. It also, DALL-E Mini is really cool and so successful because it demonstrates really impressive results at significantly less expense than its predecessors. Though the FID is not published yet due to the model still undergoing fine-tuning for the final release. That's one of the cooler things about this. They are not even done finalizing it. This is their projected timeline here. So quite a bit of work to go, but their initial version is pretty amazing. I'm very excited to see what the fine-tuned version will look like. So how was DALL-E Mini actually made? Well, the Crayon project used, as I said, it was a collaboration between Jack's team, which is Google Cloud, and Hugging Face, and they used 3 data sets to ensure the most robust model possible. They used the conceptual captions data set with 3 million image and caption pairs, conceptual with 12 million image and caption pairs, and the OpenAI subset of YFC C100M, which has about 15 million images that they further subsampled to 2 million due to limitations in storage space. They also use both the title and description as caption and removed HTML tags, new lines, and extra spaces to get a really nice, really broad understanding of language and visual features. One of the things that I was most interested in when I started looking at Crayon was JAX. For those of you that isn't familiar, JAX stands for Just After Execution, and it's a relatively recent library developed by Google Research. Unlike TensorFlow, it's not an official product, but and that has really helped it become really popular in the research community and the open source community as it has grown in stability. But really, the advantages of JAX boil down to 2 things. The first is just-in-time compilation, which is basically allows the user to capture the maximum amount of flops for generating optimized code And then it also enables NumPy code to be run on GPUs and TPUs in addition to CPUs via AutoGrad. This is their upgraded version of AutoGrad if you're familiar with AutoGrad. In tandem, these two capabilities, allow JAX to accelerate tensor operations to a huge extent compared to TensorFlow and PyTorch. I found that other than a few situations like using torch and n.linear on a very specific use case, it can be a little faster, but otherwise JAX outperforms TensorFlow and PyTorch on all the same tasks in my experience. I don't have numbers to back that up in front of me though. So the reason this is so interesting is because this was one of the key tools they used to actually lighten the model so much. The other, and we'll go into that now, was to use pre-trained models to save on the amount of training and work that needed to be done to create a massive deep model to understand things. Their ablated diffusion model is rather large in DALL-E 2. So how does DALL-E Mini Crayon actually work? We're going to start with the training, and then we'll talk about how it works for inference. First, the images are encoded through a VQ-GAN. I should start by saying this. The training process for Crayon uses a seek-to-seek model with BART to combine the textual and visual semantic information in the encoding. So the way it does this is the images are first encoded through a VQ-GAN encoder. That stands for vector quantized GAN, which turns the images into a sequence of tokens. Next, I'm sorry. I'm so sorry, y'all. I was reading off. I have my own on the other side. It is frozen. Excuse me. Please excuse me. I will go back. Okay. The training process for Crayon uses a seek-to-seek model in BART to combine textual and visual semantic information. And it also uses a VQ-GAN to encode the textual. So first, the images are encoded through the VQ-GAN encoder that's here. To turn the images into a sequence of tokens. Then the caption, so this description, is encoded through BART. And then next, the output of the BART encoder and encoded images are fed through the BART decoder, which is an autoregressive model whose goal is to predict the next token. And as you can see, it's using the VQ-GAN tokens from here with the BART decoder. And then iterated through to get to the best possible reapproximation of the beach. So this process repeats. And the loss is the softmax cross entropy between the model prediction logits and the actual image encodings from the VQ-GAN. So it'll create this modified version based on the, I guess, sub portion of the tokens with the encoding of the text, and then compare the two, and then make modifications to the generation or training as needed to get a better approximation of the original image. Next. So that's how we train the model. DALL-E Mini next uses, for inference, we are only inputting captions and we want to generate images, and it starts first by encoding the caption through the BART encoder again. So this is this final output of the BART decoder from the last slide, the best versions it will be. So we take that as our input here, decode that into sample candidates for the prompt by using a beginning of sequence token in the BART decoder. The image tokens are then sampled sequentially based on the decoder's predicted distribution over the next token. So it uses the first token in the sequence to then predict the next, and the next, and the next, and the next. And using the trained model, it is able to impart the desires of the caption onto the image. This sequence of image tokens are decoded then through the VQGAN decoder, and then clip is used to rank and select the best generated images by, just picks the top K images. And you can determine how many images you'd like that to be in the code. So there's less out there about DALL-E Mini, which is why that seemed a little shorter. Let's break down what these differences actually look like. And I'm going to focus on the inference part of the architecture here. So as a little recap, DALL-E 2, in DALL-E 2, first the clip text encoder maps the image description into the representation space. Then the diffusion prior maps from the clip encoding to a corresponding clip image encoding. And then finally, the modified glide generation model maps from the representation space into the image space via reverse diffusion, generating one of many possible images that convey that semantic information within the text caption. So a corgi playing a flame-throwing trumpet is the example in the paper. DALL-E Mini, on the other hand, starts with the caption, which is we got from our BART decoder in the training phase, is passed to a BART encoder, where the beginning of sequence token is fed through, and the image, the beginning of sequence token is fed through the BART decoder. The image tokens are then sampled sequentially based on the decoder's predicted distribution over the next token. And then the sequences of image tokens are decoded through the VQGAN decoder, and clip is used to select the best generated images. As we can see, there's some pretty significant differences between the two. And really, DALL-E Mini is completely independent in terms of architectural design from the original DALL-E or DALL-E 2 architecture. But let's list off some other things that are interesting differences that are worth noting. The first is the language it was written in. You can use DALL-E 2, and I believe there's implementations. No, it's not publicly available. So I believe it was written in PyTorch, and DALL-E Mini was written in JAX. Crayon also heavily, or DALL-E Mini, sorry, Crayon, DALL-E Mini, same thing, heavily leverages pre-trained models. So we have our pre-trained VQGAN and BART decoder and clip, while OpenAI, who developed DALL-E 2, had to train all of their models from scratch. So the Crayon model architecture is able to take into account these pre-trained models available and their efficiency to make it a little bit lighter. Next is how they use clip. DALL-E 2 uses a clip encoding with the prior ablated diffusion model, while Crayon uses BART to create the image encoding and clip to instead rank the final outputs. That's because they are not training their own clip. They're using a pre-trained. Which makes sense because the available public clip API is likely less robust than the one that they use for OpenAI's computer vision projects. I'm fairly certain that they are consistently upgrading and training their own clip dataset to get better and better. For example, it doesn't do great with facial stuff in the public API. So that is also one drawback of DALL-E Mini, is that it's using this kind of less good clip model that wasn't trained along with all of the data itself. But nonetheless, they were able to get some pretty high quality, well, not high quality, but pretty, I would say, accurate image generation with Crayon. So next, DALL-E reads text and images as a single stream of data, while Crayon splits them between the seek-to-seek encoder and decoder. So that's the BART encoder and decoder. This is what lets DALL-E Mini use independent vocabulary for text and images. I believe DALL-E 2 has to have them actually directed and inputted, whereas through the seek-to-seek, DALL-E Mini or Crayon can actually make its own vocabulary. Next, DALL-E 2 reads through an auto-regressive model while using a bidirectional encoder. And DALL-E Mini instead uses VQGAN to decode a single direction code from the BART decoder. And finally, DALL-E Mini was only trained on the 15 million or so image pairs that I mentioned at the start of this conversation about DALL-E Mini, whereas I don't have the data for DALL-E 2, but the original DALL-E was trained on 250 million pairs of images and text. So that's significantly more training on significantly more data. What is the initial, sorry, I just saw your question. What is the initial data set for DALL-E Mini? So they used 15 million images from the OpenAI subset of YFCC100M for, I believe it was, which step of training? I think it was fine-tuning their VQGAN encoder and BART, and then they use the conceptual captions and conceptual to fine-tune clip. Fairly certain that's what happened. But I may need to get back to you on that, Nicholas. Can't recall off the top of my head. Okay, so in effect, we've gone over both of these now, and we can see that there are some seriously major differences. They're hardly the same architecture. I would say they aren't at all. They just share a name. So it's been interesting seeing how these two different spinoffs of the original DALL-E came to be and how they're different. One final thing to note is that DALL-E 2 produces significantly higher quality images than DALL-E Mini. I think DALL-E Mini's outputs are 600 by 600, whereas DALL-E 2 can go all the way up to, like, I want to say 2160, but I'm not positive. I think that I think DALL-E 2 can get Ultra HD or Super HD. So really what we want to think about here is that there is a massive decrease in time and costs to train and use the Crayon model compared to DALL-E 2. The two projects may have originally shared a name, but that's really the majority of what they share, I guess, besides their subdomain. There's a lot of key differences, and you would want to use them in very different spaces. So why should you not use DALL-E Mini, which is another way of saying when should you use some other image generation model? Well, I would say you should use DALL-E Mini or Crayon if you need images generated fast, because it is fast. If you need low-cost image generation, it can do this on very little GPU compute. I actually haven't tested it on CPU, but it might be possible. I think I've run into errors trying to run JAX on CPU before, so I'm going to assume that it doesn't work on CPU, which would make sense because JAX is autograd, and that means running on GPUs. Sorry. Next, I used the word high quality. I meant like highly accurate, just to be clear. Very highly accurate scenes. So DALL-E Mini is great for doing, I was shocked. It does scenes really well. So like we can see right here, there's this top example. I mean, that horse looks like it's made of, Thank you, Ariel, for confirming that. They said that JAX can work on CPU. The question is whether it would take minutes, hours, or months. I would actually suppose minutes just for this. You'll see when we do it, it is, I mean, it's not lightning, but it's maybe 20 seconds for an image, which is pretty nice if you're used to waiting 2 hours or something like I am sometimes with some of these. The technology's come really far in the last year. And just speed overall, I think that was meant to actually refer to training. So if you needed to fine tune something, this would be a lot quicker and easier to fine tune than a lot of other models. You should not use DALL-E Mini or Crayon if you need high quality faces or human features. They talk about this in their publication, but basically they didn't include enough face feature data, and they're going to need to do more fine tuning on faces in the future. I'll show you how funny that looks when you try and do faces in a little bit. I'll answer that question in just one moment because I'm almost done with the slides. And finally, high resolution images. As I said before, DALL-E 2 can do much higher resolution images. Same with Imagen, Glide. There are a number of different models you can check out that will get you super resolution, and Crayon will not. Okay, had a question in the chat. Did you already run DALL-E 2 in Paperspace? If not, is it possible? DALL-E 2, to my knowledge, is not publicly available. I think Lucid Rains has made. If y'all don't follow Lucid Rains on GitHub, you should follow Lucid Rains on GitHub. He's awesome. Yeah, okay. Lucid Rains has implemented DALL-E 2. I thought he had, but my understanding is that it is still a significant work in progress. He has all of this information here, but I tried implementing this once and I couldn't get it to run. So he seems he's updated this a fair bit since I last checked. I'm assuming excuse me. It seems that let's see. Okay, so it looks like they're not in the process of working on a tutorial or making an additional notebook. Okay, so I would check out this. If you're interested in making this work, I would definitely recommend checking out their implementation. Maybe that could, I'm gonna work on this too. Watch our blog. I'll see if I can get something out within the next week or so on how to implement this, because this would be a fun follow-up. All right, finally, how to use DALL-E Mini. DALL-E Mini can be accessed in a number of ways. Primarily, you'll want to either run it locally, use their web app, or create your own implementation on a cloud GPU. If you're anything like me and you've been alive the last 3 years, you are not able to or don't want to spend an exorbitant amount on a GPU. So I definitely recommend the web app and or the cloud resource. One thing to note is they've kind of remedied this, but the web app gets the hug of death from all their fans. So occasionally it is down. I think they've gotten some pretty big server upgrades since they posted that, but just keep that in mind if you are going to use their website, which I will show in 2 seconds. And finally, I would say a cloud resource is probably ideal for development, as we can scale up production as needed and can do little tweaks. In this last slide, I've got some useful resources that I definitely recommend you go through, including Crayon's own web app. So this is their little web app, and all you need to do to run this here is put in whatever caption you are interested in. So I've got an astronaut riding a horse in a photorealistic style. Let's do pixel art of Super Mario Chris Pratt, because Chris Pratt as Super Mario is still incredibly amusing. Okay. Huh. So I've got a little bug there, sorry. I was wondering why that was still running. All right, so back in here, back in our notebook that we made earlier, can I get B's in the chat? Was there anybody that was able to get everything set up in time to follow along? If not, I know we're kind of running out of time, but I can quickly go back over it. Let's do put yes in the chat if you want me to go back over it. Otherwise, say nothing. One is enough. All right. So Tomas, that's cheeky. So to do this, So Mariama, let me get these slides copied again. Okay. So if you go to slide 5, you will find the instructions for setting up the notebook itself, but I'm not going to walk through that. All you need to do is make an account with Gradient, go to any project, open a notebook, make sure that it's PyTorch and free GPU, toggle advanced, and then toggle advanced options in the bottom right corner, and then paste this URL as your URL. Then once you're in the notebook, make sure that you really run all will work. We got Jax, JaxLib, DALL-E Mini, VQGAN, Jax to install. Then we're assigning some variables here, making sure that we're pointing to our GPU, installing IPy widgets and upgrading TQDM. For some reason, things were breaking without that. Then run this cell. This is where you're going to need to input your API token. You can get your API token by going to weights and biases or wandb.ai and then creating an account, then going to settings and then scrolling down to danger zone API keys. Excellent question. Yes, somebody asked if you've done the pip install steps on here. Basically, anytime you restart this, the cache isn't saving your pip installs. It's only caching the original Docker file and I think the files in the workspace. This is going to change very soon because I've been giving feedback about that not being great. But as of right now, you do need to rerun the pip installs every time you go back in this notebook. And as Nicholas pointed out, it seems the API token gets indicated in a link, which is nice. Okay, then you run this. It'll ask you to put in your API token there. Don't believe them. It did not take 0 seconds. That's a lie. Then run these. These will get our params for VQGAN set up. Then we get our model functions compiled and parallelized. Then making a random seed that we can use if we want to influence the uniqueness of how this is working in some way. You can change the seed up a little bit. Then we are getting our DALL-E BART processor model. This is, you would need to put in your API key if you hadn't already, but that shouldn't be the case for any of you. Then we are assigning our prompts here. Okay, sorry, no more rushing. We're back in it. All right, so if you got everything done, you should be about right here where we're doing prompts. I have some really silly ones, so if you want to change these, do as you please. I've got fine art painting of a foolish samurai Jack wielding a magic sword, stepping forth to oppose Aku. If any of you get that reference, you're my friend. Then Barack Obama as pixel art, and then Obi-Wan Kenobi standing over lava with a lightsaber. Tried doing Anakin too, but it was breaking, or it just doesn't do people very well. So Obi-Wan alone, he has the high ground. Let's see. And we are tokenizing our prompts with our BART processor. BART processor. Excuse me, I don't know why I was saying BART. BART, not BERT. Then some more variables to set. You can change in predictions here to determine how many output photos you're going to get. We can also customize generation parameters, and you can figure out you can find details about what these do here. I'm not going to go over it just because we're at time right now. Next, we have the generation loop here. So takes our pgenerate with all of the variables we've set to create our encoded images, remove the beginning of sequence token, and then decode the images and then display them. So I've got some examples I already made here, but I'll run it again so you can see how quick this is. So as you can see, I've kind of done all people in a cartoon here. So these are going to be pretty ugly compared to the other examples. That kind of looks like Lego, Lego Obi-Wan. this is a super inhuman face. So I think it's able to recognize the cartoon character, but it's unable to recreate it. And that's interesting. And then poor Pixel Barak failed completely here. The body of this one looks fantastic, but something happened with the head. A similar thing here. Yeah, so you can see it just doesn't do facial features very well. And there's some significant artifacting going on. Kind of blending of the generation effects across the thing. Okay, sorry, I saw your question, Zach, but I was so excited I didn't answer. Is there a way to weight words? For example, I tried a helicopter flying over a black hole, but I just see a black hole. It's an interesting question. I imagine that's a consequence of clip, actually, because clip would be prioritizing which text features are most approximating the original image or the output image. Confusing myself. So I don't think so. I think what you're talking about would require actually fine-tuning clip during training to have more or less focus on certain features, but I'm not positive. If I have a second at the end here, I will look into that more because that's a really excellent question and I want to know the answer to. General griefs. Okay, so just for the sake of having something be different, let's do. Oh, and for comparison, actually, it didn't seem to actually draw that, which is a tragedy. Maybe their application is having a problem. This is why it's better to use gradient. No application problems. Oh, Nicholas, that's a really good point. You could probably, yeah, you could probably do emphasis on the words using pointer adjectives. Like you could say like an important, I don't know who's important, an important actor. I don't know celebrities. Somebody stands in front of not important people and then maybe it would prioritize them. I'm really not sure. Oh, cheers, Tomas. I didn't notice that. Good call out. Okay, so I would have been able to see it if I didn't still have the other image blown up. Okay, that makes sense. Well, still for the sake of comparison, I'm doing Super Mario Chris Pratt. And let's run this. Ooh, what? Okay, if you run into this, just restart your kernel. It's happened to me before. You should have everything cached, so it shouldn't be a problem. Just running everything again. Sorry about that. There we go. So, as I said before, Crayon is not great with faces. I also don't think it knows who Chris Pratt is, based on this. I've done this before, and this is one of my favorite questions to ask an image generation model, because they always have no idea what to do, and it leads to some fun situations. But I would say here that it's mostly pretty unsuccessful. Combining a lot of Super Mario general features like green hats instead of red. I don't see anything curved. This one is not even Mario. I don't see anything Chris Pratt related. So yeah. Back here. All right, yeah. See, after I restarted, it's running. A little embarrassing, but some little bug with the code. And as we can see, our Crayon is doing exactly the same. Pretty ugly little Mario there. Okay. All right, while this finishes, there's one last thing to go over, but I gotta wait for this to finish running. So while this is finishing running, I'm gonna look at weighing words, weighing certain words in text input. See what they were doing. Huh. Okay. Not seeing anything there. Let's check. Not sure off the top of my head. Somebody mentioned temperature as a possibility, but I can't recall what temperature does. Trick is to make the addition sharper. Interesting. So this looks like difficult to control though. Like it's let's see. Ariel asked, in essence, are all the DALL-E X whatever models, NN models trained on a large supervised data set for mapping labels to images, right? Yeah, I would say that that's accurate. They all require a giant image caption pair data set. My understanding is that they didn't use Cocoa. You can actually see in the paper for DALL-E 2 here, their comparison. Okay, yeah, no, they did not use Cocoa for DALL-E or DALL-E 2. So they have their own custom image caption pair data set. And I think they were also using the YFCC 100. They train, all of the models train on large data sets to map the mapping labels to images. I'm not sure if that's the correct way I'd put it. I would say it's more unifying visual, semantic, and textual semantic information in a single encoding to use for generation. I'd say that's what all three of them kind of do in a way. They just do it in very different ways. So like DALL-E 2 uses diffusion to achieve that. And I'm sorry, it uses clip to achieve the original encodings and then diffusion to do the generation. And then DALL-E Mini uses BERT and VQGAN as separate components to encode the textual and visual semantic details, then combine them to be decoded by BERT to then be compared with, is it VQGAN? Remembering all of this off the top of my head. Yeah, to then be combined with VQGAN. No. Sorry. Okay, I'm getting some reports that some people have been able to get the helicopter flying over a black hole and red and black helicopter flying over a black hole in a starry sky. Okay, I think that's functional enough. So it seems that the more descriptive you are, especially of the words, it will be able to, I'm fairly certain that it makes bigrams and trigrams as tokens so that it's able to recognize the adjectives and stuff together. Can't be positive off the top of my head on that one. No, it wouldn't do that because we just have the beginning of sequence token and then each individualized tokenized word. Okay, and then it learns to predict each next word in the sentence and then uses that to predict the encoded version. Okay. It's a lot, as y'all can see. All right. So now that that's done, we can use clip to actually rank them by score. So if you wanted to know what your best image is without, just guessing by looking at it. This is how you would do it. This is the official method for ranking these. So this is how, if you were to, here we go. And you know what? I'm inclined to agree so far. No, that's the best Aku, but there's no Samurai Jack. It's very amusing. It outputs that score value below, which you can use as a means of comparison, giving us a nice means to do qualitative and quantitative analysis of how our different generated images are doing. Okay, well, with that, we are actually done. I'm sorry I went 10 minutes over. I really appreciate y'all staying so long. I've got one question here. Can you do inpainting with DALL-E Mini? Huh. To my knowledge, no. Because it's constructing the image. Let's see. Can you do inpainting with DALL-E Mini? That's a good question. I'm fairly certain that's a no. Yeah, because during the inference and generation stage, we're working with just the text caption to produce the images. So, I mean, maybe. No, I don't think so. That would, I'm sure it is theoretically possible, but it would be frighteningly complex to, you'd have to basically figure out how to create captions that would correspond to manipulating the BART encoder in such a way that, no, I don't think it's possible. So no inpainting. Stick to glide if you are going to be doing inpainting. Any more questions? Just gonna give it 20 seconds in case somebody's typing a paragraph. All right, well, I'll take that as a no. Thank you all so much for coming to today. This has been really fun. I really appreciate all of your participation and energy. Before I go, let me one last time share these slides. If you make sure you save them because they will disappear after the Zoom ends. If you want to look at this later. For those of you who weren't able to get a free GPU, remember that there will be free GPU availability going up later in the day, most likely, and probably as people get off of them right now. So if you want to try this out, you can follow along. It's well marked down, so should be easy enough to run the tutorial that they have so graciously provided for us, and I've adapted. Really appreciate y'all. Thank you so much, Nicholas, Alex, Mariama, Jose, Tomas. Tomas, I'm not positive. It depends on my editing. I would say today or tomorrow. Thanks, Jeffrey. Thank you, Juan. Yeah, Tomas, I would say either Friday or Monday. Thanks, Zach. Thanks, German? Sorry if I mispronounced. Thanks, David. Thanks, Craig. Oh, there was another question. If you haven't already left, person who asked me a question, yeah, it is possible to increase the quality of many DALL-E produced images by another model. You just need to get a super resolution GAN or something like that on it. I would say that's totally doable. Next, will we be able to get a copy of the recording? I'm gonna assume, yeah. I'm putting this out on YouTube, so everybody will have access to it. Thanks, Rita. Oh, I've got a recommendation for GPEN super resolution. That's fair. I've also had, I like GFP-GAN a lot, but you have like, that's actually like a photo restoration algorithm more than anything. I'd be super interested in what GFP-GAN would do to images produced by this. All right. Thanks again, everybody. I'm going to call it now, but I hope you all have a wonderful rest of your day. Thanks again for your time.